Hey, thank you very much. We stopped yesterday at this stage. We continue the same discussion today, mostly the example type discussion, but we discovered quite an important role of this matrix in terms of function local behavior, especially if the function you consider, especially if you consider the function near the stationary point, because when you do it near the stationary point, this is something which is well explained by the Taylor series expansion. When you study your function near the stationary point, this term is the first principle, the first non-constant term in the Taylor series expansion disappears because the gradient is 0, and the leading role is taken by the second one. And the second one is you can restructure this second term with the help of matrix multiplications. With this, we can restructure it in a way that the key role will be played by this matrix composed of partial derivatives. That's why this matrix, and we saw in a special case of the homogeneous polynomials of second order, we saw how to analyze such matrices with the help of eigenvalues and eigenvectors. That's why this matrix deserves a special name. Here it is. From now on, we're going to call this matrix Hessian, just to reflect this matrix has some other important applications, but from our point of view, just one application we discovered yesterday is enough evidence that this needs to be named for reference purposes, and we're going to call it Hessian, and that's how it is in case of n variables. That's right. Now, the other thing we discovered with you yesterday is that from this matrix, what we need in terms of classifying the stationary point in 3 subclasses, local mean, local max, or saddle point, what we need to identify the signs of the eigenvalues of this matrix. That's it. As long as we know the signs of the eigenvalues, that's all. Even the numerical values of the eigenvalues are not so much important. If the question goes just into classifying the point into 3 subclasses, local mean, local max, or saddle point. Just the distribution of signs across the eigenvalues, that's all we care about at this stage. Further information like the actual values of the eigenvalues or even the eigenvectors, they also play their own role. Like eigenvectors, they indicate the direction in which you have. For instance, if you look at the saddle point, eigenvectors, they will give you the directions in which you have either negative or positive approach. The magnitude of the eigenvalues, they will give you probably the rate of ascent in different directions. But this first principle classification into the 3 classes, all we need for that, we need just the signs of the eigenvalues. And that's a big help. Because when you look at metrics, and if you need to find the eigenvalues exactly, it may be not an easy task, especially when you look at the matrix of size larger than 2. If you look at the matrix of size 3, finding eigenvalues, it involves solving a cubic equation, which we don't know how to solve in general. If you take matrix of size 4, it becomes equation of degree 4, which we don't know how to solve in general. Yet, identifying the signs alone without the numerical values of the eigenvalues, for that task, we have very nice criteria, which will follow today. You will see them today. And they are quite doable. They're not easy, doable. They are quite intensive computational tasks, but they're still doable. Maple, with no maple, you can do it. Whereas solving a system of solving an algebraic equation of degree larger than 2, even with maple, it's not doable. Right, so this slide exactly just addresses this idea that we don't need to know the eigenvalues exactly. All we need to know is the distribution of signs. And in case of matrix 2 times 2, you can use these 2 extra characteristics of a matrix. One of them is determinant, and the other one is trace. Determinant you know more or less well. Who remembers what the trace is from the first year? well, actually, it's just set here on the slide. That's right. I mean, trace, it is as important as the determinant, even though probably in the first year it wasn't mentioned as often as determinant. Some of you don't even remember that. By no means it's the least important, by no means it's less important than determinant. It's a sum of diagonal values of a matrix. So determinant for the 2 times 2 matrix, you compute it like so. You multiply the entries across the main diagonal. You subtract the product of the entries across the other diagonal. With the trace, you just sum up the entries on the main diagonal. That's the trace. The relation of the determinant and the trace to the eigenvalues is just expressed here in these 2 lines. Trace, alternatively, you can compute the trace by taking the sum of the eigenvalues. Determinant, alternatively, can be computed by taking the product of the eigenvalues. If you believe in these 2 lines, then that gives you a very nice test for the sign distribution of the eigenvalues. If both eigenvalues positive, which is a case for the local mean, then trace must be positive and determinant must be positive, and vice versa. If the sum of the eigenvalues, which is trace, is positive, and the product of the eigenvalues, which is determinant, is positive, for the eigenvalues individually, there's no any other choice but being positive each of them. And testing the trace and the determinant, it's a lot easier than finding the eigenvalues, even in the case of 2 times 2. This actual relation between trace and determinants, I put together a little slide which explains why this is so. I'll show you this slide. Yeah. But I forgot to put the, yeah. So if you look at the matrix of size 2 times 2, you can basically name all the entries with the first 4 letters of the alphabet, A, B, C, D. We all know the algorithm which leads us towards the eigenvalues. We have to find the characteristic polynomial, right? Like so, which in this case will be a quadratic polynomial. You can basically just express this polynomial in terms of this little a, b, c, and d. So here's my determinant. We know how to compute that product across the main diagonal and take the product across the other diagonal. That's the computation. I do the expansion, and I see my polynomial. As easy as this. This bracket, a plus d, on one hand, it's the sum of the main diagonal entries. This is the trace. On the other hand, from Vieta's theorem, from the elementary algebra, we know that the sum of the solutions of the quadratic equation equal to the sign next to the linear term with the opposite sign. So the sum of the eigenvalues, which are the solutions to this equation, they equal to this bracket, which is a trace. And this is the formula for the determinant, isn't it? That's all there is to it. Very simple algebraic link between the trace and determinant and eigenvalues. That's the form my equation takes. If you use a trace and determinant symbol. And so here's your very simple analysis. If lambda 1, lambda 2, your eigenvalues, they will be both positive if and only if both trace and determinant are positive. It's if and only if result. And you can test for positiveness, which is equivalent in our current discussion, in our current context, to local minimum point. You can test trace and determinant. They're both negative. If and only if, what should be said about trace and determinant? Both negative. Negative, what is negative? Trace is negative, obviously, because some of the 2 negative values must be negative, and and determinant positive, because you have two identical product of the two negative values gives you a positive value. Trace should be negative, and determinant should be positive. And two eigenvalues being negative, that's the case for local maximum point. If you have different signs, one eigenvalue positive, the other is negative. If you have different signs, probably it's not a good idea, I'll just like this. Say lambda 1 is positive, and lambda 2 is negative. What should I say on this side in terms of the trace and determinant? Determinant is negative, thank you very much. Trace? You shrug, you just... Well, we don't care actually. Because just determining being negative, it's already enough evidence that the eigenvalues are of opposite sign, no matter what happens with trace. Just this one alone, it's enough evidence for, in our current context, it's enough evidence for saddle point. Right. And that's the little slide which explains the link on my main set of slides between the eigenvalues and trace and determinant, which will save a lot of time to you, for you, because otherwise you would need to go through the solution and everything. Right. Well, now the following few slides, I just take our these 8 functions we did like manually, like we did by hand yesterday, and they just apply the same logic. They now apply this new logic with the Hessians in eigenvalues, and we see if we have the same result. So the first 2 functions we had, there were 2 canonical functions. One was elliptic paraboloid, and the other one was the upside down elliptic paraboloid. For these 2, if you build the matrix, it will be diagonal one. I mean, if you compute partial derivatives, if you just compute these partial derivatives for this matrix, that's how it will be. 2 diagonal matrices for which trace, determinant, or direct knowledge that for the diagonal matrix, diagonal entries are the eigenvalues. It's one of the great advantages of having diagonal matrices. For them, we don't need to do really heavy spectral analysis. Every diagonal entry, it is the eigenvalue. It just gives you the answer because we have 2 positive eigenvalues here, 2 negative here. That's why we have on the left-hand side, we have mean, local mean. On the right-hand side, we have local max. The other examples from yesterday, again, all of these Hessians, so all of these partial derivatives, second-order partial derivatives matrices computed. The example 3 and example 3, let's just look at that first. Diagonal matrix, 2 eigenvalues of opposite sign, saddle point, and we're clear on that. Even the graph was very clear on the saddle point. XY, we had a saddle point, even though this time you no longer can see the eigenvalues from the matrix straight away because it is no longer diagonal one. But if you do, for instance, trace and determinant analysis, trace of this matrix of the number 4, trace is 0, and determinant is -1. That's the last case on my dynamic slide. Negative determinant, eigenvalues of the opposite sign. This slide actually gives you the actual values of eigenvalues, 1 and -1, but they are irrelevant for the conclusion that this is a saddle point. What is relevant is that negative determinant. Example 5. That's an interesting one. That's the first example where it looks like we don't know what to say because one of the eigenvalues ended up 0, which again you can see in the trace and determinant language, because determinant of this matrix is 0, meaning if you remember that determinant is a product of the eigenvalues, one of the factors there must be 0. What do we say in this case? Well, this is a subtle case, as a matter of fact. When one of the eigenvalues ended up 0, this Hessian term, this second term in your Taylor series expansion, it is no longer the driver. it loses the ability to be the driver, to be in control of the behavior of the function. So in this case, this analysis is useless. And these two examples here just convince you that this is true, because look at this. We got example 5 and 6. On both occasions, we have a presence of 0 eigenvalue, but the conclusions are totally different. Here, in this example, if you remember, we had the local mean. It was quite obvious from the very elementary considerations. Function is always non-negative. Here, we had a saddle point. We presented explicitly two different approaches, which we gave us negative and positive approach. Which means eigenvalues, they no longer distinguish the behavior of the function if one of them is 0. Yes?
We then go to the third order derivative.
I didn't catch that.
Can we then go to the third order derivative?
Well, I was about to say that. That's right. So in your Taylor series expansion, this second term, the Hessian term, which is built around the second order derivatives, it's no longer important because of the 0 there. It becomes negligible as much as your gradient was negligible because the gradient was 0. And you have to do the analysis already on the third level, on the level of the third order derivatives. Although we're not going to do that because it's already a higher level analysis and we don't have time, and plus probably it's a little bit beyond this level, our level of understanding, to do that sort of analysis. But at this point, what you have to remember is that if 0 comes up, the Hessian analysis is no longer helpful. You need something more subtle, more advanced to do the analysis. Eventually you will learn it. In this case, probably it will never happen unless like in these two cases, in the case 5 and 6, you can determine the behavior by some other straightforward elementary methods. In the case 5 and 6, we can do it by just exploiting some other properties of the function. Here we exploited the fact that the function is clearly non-negative. Here we exploited, we didn't exploit much of the fact, but we just tested a few directions, just guessed them, and they worked for us, which is we're lucky to some extent. On example 7 and 8, that's where we discovered the Hessian, the sort of the simple version of the Hessian analysis first. Basically, if you do the full Hessian analysis with the partial derivatives, you will end up with the same matrices and the same eigenvalues as before. But again, remember, in principle, you don't need to know the numerical values of those eigenvalues if the question just goes classify into subclasses. If you need to classify into subclasses, all you need to know is distribution of signs. Any questions? Okay. Now, I think the rest of it, yes, well, the rest of it, actually this slide in particular, it gives you the analog of this determinant trace tool, good tool, very effective tool, in case you're looking at the matrices of higher dimension, higher than 2. When you have dimension higher than 2, finding eigenvalues, it becomes really hard business. But remember, we only need the distribution of signs. Trace and determinant, just these two, they are no longer enough. But what is enough is just this theorem at the bottom of the slide. Sylvester's criterion. And look what it says. That's the one which is good, and that's the one which you're going to use. We're not going to prove it. It's a really tough proof. I saw it probably only once in my life when I was a student. We saw the proof back then. It's not an easy one. But it's right now it's irrelevant. We'll just first try to understand the statement of it. Well, first we have this beautiful definition, just to ease the language a little bit, or just give you some alternative way to say things. So, because it is, well, all what we just doing right now is spinning around this classification of a matrix into those which have only positive eigenvalues, only negative eigenvalues, or neither of those. We're going to give some names to these subclasses of matrices, and these are the names. So positive definite, we're going to call a matrix positive definite when every eigenvalue is positive. As simple as that. We're going to call it, obviously, negative definite when every eigenvalue is negative. It's a third line in this definition. If eigenvalue is allowed to be not only positive but 0, we say positive semi-definite or negative semi-definite. And this Sylvester's criterion it just gives you the computational test how to verify that the matrix is positive definite or negative definite. Again, going for eigenvalues, it's no longer a choice if you go for the dimensions higher than 2, because finding eigenvalues, you can't do it. Not every equation of degree higher than 4 is solvable, especially analytically solvable, I'm sorry. So Vestas, I don't know how he come up with that, but it's a beautiful result. He restates this positive definiteness and positive negative definiteness in terms of determinants, not just one this time. In case of 2 times 2, we had only one determinant. Here we have plenty, like the whole n sequence of n determinants. Which ones? Well, this line says upper left k times k submatrix. I think it's very clear what they mean here. So you take your huge square matrix and you take submatrices which are just sitting in the upper left corner. The very first one of size 1, when k is 1, it will be just one single entry in the position 1, 1. The number 2 for k equal 2 submatrix, it will be the one which takes the element 1, 1, 1, 2, 2, 1, and 2, 2. The third one, it will be the 3 times 3 square in the upper left corner of your matrix. So you take all of this. Altogether you have n. You take all of these submatrices. For each of those submatrices, you compute determinant. At this stage, you're already just probably horrified how much you have to compute. Yes, that's how much you have to compute. But the good news is it's so doable, unlike eigenvalues, which are not doable. It's a computational task. Maple, any other way, it is doable if you go Sylvester's criterion. And the test itself says, if all of these submatrices, I'm surprised this definition actually doesn't say, I mean, there is all of these submatrices, the determinants of those submatrices, there's another name for that, it's called principal minus. Yeah, but never mind that. We can use this language. So if the determinants of all of those submatrices are positive, all of them positive, that's the case for positive definiteness. If and only if, you see? If they have alternating signs, it's this line, the third line here. And you have to be careful which way you alternate. It's not like any alteration. The alteration should go, the very first determinant, which is basically one number, must be negative, and the others, they alternate plus minus plus minus. If you have such a case, so the very first one, you see the odd one, it's negative, and for even ones, it's positive, so you have a perfect alteration with the one, with the negative, with the negative being first. It is the case for negative definite. That's right. And that's basically, this is it. Well, there are the cases for the positive semi-definite. It's when you allow to be 0 for some of the determinants, but this time it's no longer a reversible criterion. It's only one way, but still you have it. And that's the one which you can use to classify the points in case you have function of more than 2 variables. Because in that case, your Hessian will be of size more than 3, and you don't have any other way but the Sylvester's criterion. That's right. I strongly encourage you to use Maple. I don't see the point of torturing yourself in all of these numerical computations with a pen and a paper. Once probably you can try to do it if you like challenges and you have lots of paper. Otherwise, you're free to use Maple or any other computer algebra system. There are plenty of the computer algebra systems freely available. I mean, you don't have to pay. Does it cost much, Maple, for students?
Yeah.
It does, because I never had it. Well, obviously, in the labs here, you can do Maple in the labs, but you have, I don't know, do you aware that there are lots of systems which are fully capable as Maple is, or as Mathematica is, especially for your level, which are freely available on the net? Freely, I mean like it's the open source and everything. Who knows any system like that? Does anyone know in this class any system like Maple which is freely available? Does anyone suspect that they exist?
I don't know them.
I didn't catch who. You said you don't know them. There are plenty. I know. I'll show you if you. For a while, I was using this one, but it's a quite old one. It's the one which was once written in MIT, and then here we go. It's not the best currently. I mean, there are more like a better developed currently, but it's the first one I know. There's another one which is called Octave. Yeah. It's this one. It's another one which is good. And there is a third one which I never managed to make running on my computer, but I never really probably tried hard enough. It's called Sage. Well, you have probably say Sage Computer Algebra System. I like the spinning disk. Is it gone? Thank you. Computer Algebra System. It's a free, which I know, Sage Math, yes, open source mathematical software system. It's a free, which I know, so if you don't like Maple, if you don't have it on your own laptop, that's a free options for you, which as good as those. I mean, the syntax of the commands a little bit different, but not much. And you can use them for your computations. Right, okay, back to the slides then. Now, all right, so let's just see what we have else. Well, this is just a sort of a corollary, which just links the positive definiteness to local max, local min. So positive definite, all positive eigenvalues, it's a local min. Negative definite, all negative eigenvalues, it's a local max. The opposite criteria, the less, probably less often used, but why not stating them? It's a little bit harder actually what happens with the saddle point. I don't think it's an accident that the theorem the previous theorem and this theorem doesn't really touch this subject. We certainly know what happens when we have function of two variables, because in that case we know this determinant negative, that's a saddle point, if and only if. For the function of three variables, it's a good question actually. I mean, it's a good question whether you can classify a point into a saddle point just using these determinants from the Sylvester's criterion. You can classify point into local max, you can classify in local mean, but the saddle point, I'm not sure. It most likely for the saddle point, if it happens, I'm not sure if it happens in your experience in this topic, whether you will see a function of three variables where a saddle point will come up, and whether that will be, you won't be able to see the saddle point by some other elementary means. I'll look for the examples, and if I find any interesting, I'll discuss it in class. But from right now, if you ask me what to do in that case, the only solution which I see, you have to find the eigenvalues numerically and see if there is a positive and negative there. Okay, if Sylvester's doesn't work for you, and you can't classify a point into local max and local mean for the function of larger than two variables, at that stage right now, all I see that you have to go through eigenvalues. If there will be an example of this level, I certainly will bring it up in class and we'll discuss it. Well, this is just a computation slide. Again, we're back to the two variable case. It's a very easy case now after this. Yes?
That slide before, what's the significance of denoting f at c squared?
That's good that you bring this up. It's just a notation which says f is twice differentiable, twice continuously differentiable, which you obviously need to have, otherwise you won't have partial derivatives of the second order. So this symbol c with a super index, it just tells you how many times function is differentiable, how many times function is continuously differentiable. C is for continuous. That's right. So C1, it's a function which is only once continuously differentiable. C2, it's a function which is twice continuously differentiable. I'm sorry, I overlooked this symbol. That's what this symbol means. Yeah. So the next slide is basically, it brings us back to the two variable case, in which case, in such a case, the analysis now, in comparison to Sylvester's approach, it's a piece of cake. You will love it. I mean, I trust me, you will love it after you do once 3 variables, especially by hand. Here we just need to compute determinant in the trace, and that's a determinant. Now, is expressed in terms of the partial derivatives, and that's just your Sylvester's criterion in terms of these determinants. And a special case for the saddle point, you see? The case we no longer have for the free and more number of variables. I'm just hoping there will be an example. There will be an example eventually. I'm just looking for it. Yeah, it's the example. It's a typical example you will once have in this topic, and you have to, well, you need to know how to do it. Function which you need to analyze for, I mean, you need to find all of the stationary points. I had a pause because I was trying to remember the right definition, stationary, critical, whatever, but stationary point, that's right. You need to classify all of the stationary points. First, you need to find them. Stationary points are those where gradient is 0. At this stage, you just need to solve 2 algebraic equations simultaneously. Here they are. It's the first partial derivative with respect to the x. Second partial derivative. We don't have like a uniform method to solve these sort of equations. Every time the equations normally suggest a way to do it. For instance, here, very clear suggestion comes from the second equation. We can express one in terms of the other because it's a linear one. So that's what is done. That is exactly what's done here. Y in terms of x, and then substitution in the first one. A bit of the arithmetic skipped, but if you substitute this into the first one, it will be quadratic equation. That's a factorization of this quadratic equation, and here you have your solutions. X equal 1, y2, x equal 3, y6. 2 points of interest. 2 points where gradient 0. 2 points we classify as stationary points. Now each of them needs further classification into local max, local min, or saddle point. And for that, we will compute the Hessian at every point. And that's the content of the next slide. Yeah. So analytically, that's the expression for the Hessian. All three partial derivatives, they are here. Across the other diagonal, they are identical because we have mixed derivatives coincide. That's the Clairaut theorem. So Hessian at the first stationary point 1, 2. Numerically, it's right here, right? Yes, 18. The rest are constants. It's the Hessian in the other one. It's, if you put 3 across here, yes, it's 30. That's right. So all we do now, we compute, well, here we have a second determinant, negative, which is a case for the saddle point. Here we have second determinant positive, and the first determinant positive, and the trace positive, whichever way you do it. It means that all of the eigenvalues positive here, and that's the local mean. The analysis is over. That's right. As simple as this. Just look, it's another example. Well, this time it's a function of 3 variables. Let's just see if we have some non-trivial case when we have to analyze for saddle point, because here saddle point is still a mystery, even to me probably. So, well, it's a gradient, gradient equal to 0. All of the partial derivatives here. I'm not going to verify the arithmetic, which is we're going to trust the slide. Like I said, we don't have a way to solve systems of equations like this in general, but normally the equations themselves suggest a way to do it. Here, the solution goes like this. We have a first equation where we can factorize, and from here, first equation suggests already the values, 2 possible values. First value y equals 0 because product equals 0 when every one of the factors equals 0. And here we have 2 factors, y and x take 1. So now we have a split solution in two branches. First branch is the assumption y equals 0, in which case the other two equations, they take some simpler form right in here. Third one, if you put y equals 0, you end up with z equal 1/2. That's true, I agree with that. In the second one, if you put y equals 0 across it, it will be quadratic with respect to the x. X squared take 2x plus 1, and that's a perfect square, by the way. X take 1 squared. No, wait a sec, I just miss. No, wait a sec, I'm sorry. I made a mistake. When y is 0, just only one term disappears. It's not a perfect square, I'm sorry. But we know the value for z also, it's 1/2. So it's actually x squared take 2 take, actually that's it, because negative 1 plus 1 is 0. So you end up x squared take 2x equals 0, which factorizes into two factors again, x equals 0, x equals 2. These 4 points which come from the first branch of analysis. Sorry, 2 points which comes from the first branch of analysis. Now second branch, from here, x equals 1, you do similar thing, you put this 1 across the remaining equations. Across the second equation, x equals 1 gives you this one 1, this is 2, so actually constants are gone. Yes, and you factorize the rest into z equal 0 and y equal 1, I agree with that. So well, that's another branching, right? You have now, you have to consider these two sub-branches now. And that's what's done here. Z equal 0 branch with the third equation gives you y equal to this value, right? Z equal 0. It's a quadratic equation with respect to y. These are the solutions. And y equal 1 branch with the third equation, 1 here and 1 here. I can believe that, z equal 1. So another 2 points in this part of the analysis. Altogether 4 stationary points. For each of the point, you need a Hessian. Yeah, it's a lot of computations. Here's a Hessian analytically. And on these 2 slides, we're going to compute the determinant. I mean, we didn't compute the determinants. Most likely, Jonathan Kress, when he was putting this together, he used Maple for that. And you can do that as well. It's a good practice with Maple. You can define a function in terms of x and y, which is a Hessian analytically, and then you sub in that function your values. Actually, it's supposed to be z here. It's a typo, because we're in case of 3 variables. It must be x, y, and z. Hessian depends on z. Right, so you can do it with Maple. I strongly recommend you doing this with Maple. That will boost your Maple skills a lot. You shaking your head? No? You disagree? Okay. Well, if we trust the slides, that's the values for the determinants. And from here we can see if we... Actually, that's a settled point here. It said right here. Let's just analyze this closely. Well, first I rule out the right-hand side. All positive determinants by Sylvester's criterion, all eigenvalues are positive. It means it's a local mean point. Here it is. The slide actually even says the eigenvalues, which were found probably with the help of Maple again. Yeah. Now here, let's just look at this one. The first determinant is 0, -4 and -8. We no longer have all positive. We no longer have sign alterations. So it's clearly neither local mean, local max. Yet the slide claims it's a saddle point. Well, I suspect it claims because of that. Yeah, that's what I was telling you. In case 3 by 3 matrix or 3 variables, saddle point doesn't come up nicely in terms of the determinants. You need to know numerical values of the eigenvalues. So determinants, they suggest it's neither one nor the other, but it doesn't yet mean it's a saddle point. There may be still the case where if, for instance, one of the eigenvalues is 0, that is the case where our analysis doesn't work entirely. But in this case, because with help of Maple, most likely, we found the eigenvalues. Actually, when I say, you should take it, when I say that when you have 3 times 3 or larger matrices, you can't find the eigenvalues. When I say so, I mean in general, we don't have a general way to do it. In this topic, if you've come face to face with such a problem, the equation for the eigenvalues you will come up with, it will be solvable, because we normally offer only the equations with the numerical integer solutions. And one way or another, one of the easier solutions will be either suggested or very clearly seen from the equation, and the others you can do by factorization. So in general, yes, you can't find the solutions, but in this topic, if you have a question like that, eigenvalues probably can be found analytically. Most likely they can be found analytically. That's right. Well, that's only 2 points. We have another 2, and I guess this is a killer. Well, that's the case where you certainly can't do much. Most likely this is done by Maple. This point, it's another saddle point, and again, determinants by themselves, they don't suggest that. You see, we don't have any sign alterations or anything like that, or positive signs all the time. It is by looking at the eigenvalues, we can conclude that it's a saddle point. In this case, it's another saddle point. Again, determinants, they don't suggest much. And in this case, it's another saddle point. But like, again, just keep in mind, the slide or me concluding it's a saddle point, not from the determinants. We test determinants because we're hoping it will give us either sign alterations or all positives, in which case we can stop the analysis. The answer will be clear. But if this doesn't work, we need to go eigenvalues. That's right. You know what? Well, I'm lying a little bit, of course, here. Now, I am lying a little bit, of course, here. Now, it just occurred to me. One extra fact which we didn't discuss, but if you know this fact, then you can claim that I'm lying to you a little bit. Actually, you know this fact. You know very well this fact. I'll try to bring this up in your memory, in your memories. We have 5 minutes for that, and that's the last slide anyway, and we're going to finish at this. Remember in the first year when you discussed determinants, remember there was such a result which said when you take a matrix, square one, right? And when you do elementary row operations on that matrix, you know, when you do Gaussian elimination, as long as you're not scaling rows, as long as you do only the elementary transformation of the second kind, you know, when you take one row, multiply by something, and add to the other row. Do you remember that? You should remember this very well. You've done it like 1,000 times last year. When you do this, what happens to the determinant of a matrix? Right? Nothing. I mean, yeah, that's right, nothing. The determinant doesn't change. But in the eventuality of this process of the Gaussian elimination, you will end up with the row echelon form, correct? You can even bring it to the reduced row echelon form. However, in case of square matrix, reduced row echelon form is just a diagonal matrix. Do you agree with me? Right. So on one hand, if you do operations on a square matrix, that doesn't change the determinant. In the end of this process, you will end up with a diagonal matrix. And the final question to you is this. For the diagonal matrix, what's the determinant? Product of the entries on a diagonal. Actually, I have another question. For the diagonal matrix, the eigenvalues, the diagonal entries, isn't it? So all of this, just to show you one little thing. The determinant of a square matrix of any size, it is always the product of the eigenvalues. And that's why, because the third determinant here, the third determinant here, and the third determinant here is non-zero, it means that in the product of these eigenvalues, there is no zero. So this is the really bad case where the Hessian analysis doesn't work. The bad case when one of the, or a few of the eigenvalues are zeros. This case doesn't appear in these 3 examples. Because if it was, the very last determinant in the Sylvester analysis will be 0. It's a product of the eigenvalues all the time. And that actually great. Now I see this is a big help, because we now can rule out the possibility of this really bad possibility where the Hessian doesn't work. Because of the delta free every time non-zero, we can be sure that every eigenvalue is non-zero. On the other hand, because we don't observe positive signs or sign alterations, we can also rule out the possibility of the all positive or all negative eigenvalues. And that's why we have both negatives and both positive eigenvalues. With this extra comment, I take it back what I said before. By looking at these determinants, you can decide the saddle point. Good news for you, it will save you a lot of time. Yes, that's right. I'd say yes too. Any questions? That's a very important point, that the product of the eigenvalues, it is always the determinant. In 2 times 2 case, we saw very simple analytical justification for that. In the higher case, in the larger case, the justification will go in line with what we just discussed via Gaussian elimination and this knowledge we know in the first year.